Common storage systems. The size and the type of storage systems required varies based on the features of a particular plant. The major factors to be considered are heat energy requirements of the plant, land area availability and its location, fuel moisture content, fuel preparation requirements, reliability of wood fuel supply system, weather severity. The major biomass storage systems used for the storing of biomass at commercial scale are open storage, tarped storage, permanent structure storage, anaerobic storage and silos. Open storage. Open storage involves the storage of biomass in open areas with or without any covering. This method is commonly used for the storage of grasses and agriculture residues. Biomass stacked as hay or bale stored in open areas has high chances for degradation. It can be seen that biomass stored in open areas undergo loss in net available energy as a function of storage time, and it is also influenced by particle size, air velocity and layer thickness of biomass. The table depicts that the lowest energy loss and dry matter loss was found in the chunkwood pile stored under cover. Also, studies confirmed that high energy and dry matter losses may occur in outdoor storing in small piles due to microbiological degradation of the material. The primary cause of depletion of available energy of openly stored wood fuel is an increase in surface layer moisture content due to precipitation. Once saturation of the surface volume is achieved, future weather conditions will not affect moisture content in this outer zone. Thus, construction of conical piles of biomass will minimize surface volume to total volume ratio and consequent increases in net moisture content, and thus minimizes any decrease in available energy. The secondary cause of available energy depletion is loss of volatiles and biochemical oxidation, accounting for perhaps 15% of loss in available energy. Such losses are tempered by the poor airflow characteristics typical of most piles. This chimney effect contributes to high internal pile temperatures. Of course, the high internal pile temperatures can contribute to significant moisture content decrease in the central zones. Tarped storage. This method consists of covering the biomass feedstock with polyethylene fabric sheets. This prevents entering of water as well as prevents the direct hitting of sunlight into the feedstock. Avoiding the entering of water into the feedstock can prevent growth of biomass degrading microbes to some extent. Now, the degradation will be governed only by moisture content initially present in the biomass. Tarped storage can also prevent the auto ignition of biomass caused by the overheating of biomass when it is directly exposed to sunlight. One of the major disadvantages of this method is that the tarp used for covering will prevent the escape of water vapor from the biomass, and this water will remain in feedstock, which lead to spoilage of biomass. Permanent structure storage. Storing biomass in permanent structures can provide more protection than open or tarped storage system. Unlike tarped storage, permanent storage provides proper ventilation that allows the escape of moisture from biomass. Depending on the feedstock to be stored, permanent storage is of various types. Hoop barn is the common example, which consists of half-circle steel hoop rings covered by polyethylene sheets. A permanent steel building provides more durability than hoop barn, even though it is more expensive. Hay sheds having one side panel along the roof is used in regions with low precipitation. Anaerobic storage. This is a common method used for storage of wet biomass. This kind of biomass is more susceptible to microbial attack due to its moisture content. In addition to moisture content, presence of oxygen is also an important factor that favors the growth of microorganisms. Typically, microalgae biomass can be effectively preserved through wet anaerobic storage, limiting dry mass loss to below 10% over 6 months with minimal degradation of carbohydrates and preservation of lipid and proteins. Techno-economical analysis indicates that wet storage can reduce overall biomass and fuel cost compared to drying and dry storage. Anaerobic storage can be performed with some additives and without any additives for simplest treatment. Particularly, sulfuric acid is used as chemical additive, which has potential to preserve biomass at reduced pH and to enhance lactic acid fermentation. Lower pH limits microbial activity responsible for degradation, and sulfuric acid hydrolyzes carbohydrates to monomeric sugars, making them available for fermentation to organic acids, and also ensures that pH remains low. Sulfuric acid treatment has the added benefit of being compatible with algal biomass conversion process that pretreats algae biomass to obtain fermentable sugar. To enhance stability in analogous fashion, a commercial enzyme cocktail containing glycosidase, specifically cellulose, beta glucosidase and hemicellulase are also utilized to release monomeric sugars from complex biomass. Silo. Silo is a common biomass storage system used to store grains, wood chips, sawdust, etc. It is a large concrete tower with relatively smaller diameter and volume that ranges from 1000 to 3000 meter cube. Anaerobic storage is commonly done in silos and the stored product is called silage. The major advantages of storing biomass in silo are: construction of silo requires less space. It has an option to control the temperature, aeration, moisture content, etc. inside the silo to provide optimal conditions to store biomass. There are different types of storage silos: tower silos, bale or tube silos, and horizontal or flat silos. The tower silo is a standing cylindrical container. The material is filled from the top and hence can be well compressed and stored in a airtight manner due to its own weight. Despite this advantage, the construction cost for such a silo are very high. In bale or tube silo, bales are rolled up, compressed into either round or a square shape. The bales are then completely wrapped individually in a foil by using another machine. In a tube silo, the material is pressed into a long tube. This process using a special press became common in Germany only at the beginning of 21st century. In contrast to bales, the silage of tube silo is not easy to transport, but the material takes less space. Further, less foil is needed for wrapping. The horizontal silos is the type of silos most often used to store co-ferments. The silo is constructed at ground level on fixing ground with walls on three sides. The material is fed horizontally, compressed and tightened with a special foil. The bottom layer of the foil is a thin cling foil which is stuck by remaining aspiration of the ferment. That layer is covered with thick black or white cover sheeting with webs to avoid damage by birds. It is weighed down with wires or sandbags.